Okay, 4.4 day 4, net change. So let's look at what we've studied in section 4.4 alone. So, fundamental theorem of calculus. To evaluate a definite integral, we find the antiderivative, plug in the upper boundary given, and subtract the value of the lower boundary into the antiderivative. The second fundamental theorem, that enabled us to derive an antiderivative. So if we have okay, this was equal to, I'm going to call this u. So u, and u would be in terms of x. So the derivative and the antiderivative cancel each other out. Into the function, we replace whatever the upper boundary is. So let me clean this up. Whatever that function in terms of x is, and then we multiply by whatever the derivative of that boundary is, that function u. And a had to be a constant. Then we looked at the mean value theorem and the average value theorem. So the mean value theorem this gave us the where. So where the mean value rectangle. Okay, so where the mean value rectangle intersected the function. That told us where that occurred. And the average value, if we take the mean value and divide both sides by b minus a, the average value gave us the height of what the book referred to as the mean value rectangle. So there's a lot of information in this one section alone, and it's information that you will continue to use throughout the rest of the year. All right, so our final day, net change. Okay, so what is net change? If I look at, and this is set up specifically, okay, let's, f of x is the rate of change of some quantity, of a given quantity. All right, rate of change. That should in your head, what's a rate of change? A rate of change is a derivative. Okay, so keep those things organized. F prime of x would be the rate of change of some given quantity. Well, if we take the antiderivative of f, big F prime, that would give us big F. And by the fundamental theorem, we plug in the upper bound and subtract the value we get on the lower bound. Okay, so what is this? We know that when we use the fundamental theorem, this value can be positive, negative, or 0. So what does that represent specifically? Whatever this quantity is, positive, negative, or 0, represents the net or total change in some quantity, in a given quantity on the interval from a to b. So this isn't anything new. You find an antiderivative, you plug in the upper bound and the lower bound, but now it's saying when the integrand represents a specific rate of change, then whatever that answer is from the fundamental theorem gives us specific information about the quantity we were looking at to start. So let's look at a graph real quickly. All right, so let's call this f of t, where my function represents, we'll call it gallons per minute. So let's say a barrel is being filled at a given rate, and so our unit of time would be minutes. Think about if I asked you to find this area. So from a to b, you would set up the integral a to b of this function f of t with respect to t. Sorry about that. Now look at the units only. All right, I don't give you a function. I don't give you any numbers here. If we think about how we approximate the area of a region, we use rectangles. Well, what would the rectangle be? The width of the rectangle would be measured in minutes, and the height of the rectangle comes from the value of the function. Well, the value of the function is in terms of gallons per minute. So if you just look at the units, what would these do? The minutes would cancel each other out, and our final answer, if I were to ask you to integrate the function, the units for it would be gallons. So check out what this means. Net change. Here's the rate of change of a function. So again, the volume of a barrel is changing in gallons per minute. If I wanted to integrate that function, then my final answer would be gallons. So what would that answer represent? It would be the total change in the volume of the function. And we'll look a lot more at this, okay? But just check out what the units do. When you find the area, length times width, the units of time cancel each other out, and then we're just left with this quantity. So what would that represent? It would be the total change in this quantity for this given function. All right, now let's look specifically at velocity. So specifically at the integral of velocity. Okay, so we already know the relationship. We derive position to get velocity, derive velocity to get acceleration. If we started acceleration, we integrate to what I always refer to as sort of go backwards. Okay, so if we look specifically at velocity, antiderivative of velocity is the position function. So it would be the position function at B minus the position function at A. Okay, again, using the fundamental theorem of calculus. Now what this represents is called the displacement. So the displacement is the net change, the net or total change, specifically in a position function. Okay, so displacement is the net or total change specifically in the position function. So what does this mean? It's the change of some particle from wherever it starts. Now, I said, and we know, this value can be positive, negative, or zero. If the displacement is positive, that means the particle has moved to the right of its starting position. If displacement is negative, the particle has moved to the left of its starting position. And of course, if displacement was zero, there's no change in position. Okay, so let's look at an example here. A particle is moving along a line. So that its velocity is given as t squared minus 4t plus 3. That's measured in feet per second at any given time t. And we'll use this function again. So find the displacement of the particle on the interval from 0 to 4 seconds. Okay, so displacement, that's just the specific antiderivative of the velocity function. And I'm going to have you find this answer for me. So antiderivative, and then plug in 4, subtract the answer you get when you plug in 0. Okay, and then we'll talk about this in class. Try and answer it if you can. If the initial position of the particle is at 3, what is the particle's position? Oh, sorry. At 4 seconds. Okay, so find the displacement of the particle, antiderivative, plug in 4, subtract the answer you get when you plug in 0, and then using this information, try and answer the question. If the initial position of the function, the particle was at 3, what's the position after 4 seconds? Okay, so if displacement is net change, then how does that compare to the total distance traveled? All right, so think about this. We start here. If I travel 2 units to the right, but then I turn around and travel 2 units back to the left, my displacement is 0. According to what we've said, there's no change in position. We started and ended in the exact same spot. How far did we travel, though? That's a totally different value. We went 2 steps to the right, 2 steps back, so we've traveled a total of 4 units, 4 steps in this case. So remember from your Chapter 3 test, when your velocity is positive, your particle moves to the right. When the velocity of a function is negative, the particle moves to the left. So it's this case, this motion to the left, that we have to take into consideration when we determine total distance. So total distance is found, it's the antiderivative of the absolute value of the velocity function. So think about, if this is the motion of a particle, then what we need to do when that value is negative, you have to, the absolute value would make those y values positive, and then the total distance traveled and the displacement would be 2 completely separate values. Not always, but they, if there's any region where the velocity is negative, it would make the displacement and the total distance different values. Okay, for time's sake, just copy this down, part C. Find the total distance traveled by the particle on the interval from 0 to 4. So this is where we will start our next class. All right, so you have to complete for me. Find the displacement. So evaluate this definite integral, attempt to answer part B, and then we'll start class with part C.